Go! All right. So, alkynes look really similar, and there's some similarities to the way that they react compared to alkenes, but we're going to go into quite a bit of detail of how they're different and how they react a little bit differently. And then we're also going to start to answer a question that happened weeks ago, considering what do we do when we have multiple functional groups, because we finally have enough functional groups where we can address that question and add another layer of complexity to nomenclature. So, which is everyone's favorite thing. So let's start with nomenclature and get it out of the way. It's like eating vegetables first, right? Somebody reloaded this classroom with new, it's the little things that you get excited about, right? So a couple of common names. Alkynes have a really unfortunate, I'm going to steal the book's term, unfortunate common name. Because this is ethine. So it's your ethane base, 2 carbons, and then you name for the functional group with ine. Which is easy to mix up with ene when you're saying things quickly. So we have ane, ene, and ine, which just means you have to focus on enunciation a little bit more closely. Now, ironically, this is acetylene. So if you're cutting something with an acetylene torch, you're using an ethine, but the common name is ene. Sorry. Yeah, it doesn't make any sense. There's no rationale for it at all. But here we are, having to memorize it. So other than acetylene, which is by far the most commonly used common name, there's a couple other. There's ethylacetylene and ethyl methylacetylene. And all that is tacking methyl groups on the side here. So if we have, let's see here, that doesn't work at all for let's put it this way. So this will be for a common name, ethylacetylene. If we put a methyl on this side, we'd have ethyl methylacetylene. So common names, we don't have that many to pay attention to, and by far the most commonly used one is just acetylene. But so that makes it easy. We're going to focus primarily on the IUPAC nomenclature versus common names. There's 2 terms that are actually probably worth looking at. Let's do ethyl methyl real fast. So this is ethyl methylacetylene. There's 2 classes of alkynes that we're generally going to pay attention to. This is a terminal alkyne because it is at the end of a carbon chain. It doesn't have any R groups on both sides, just a single hydrogen on one side and then an R group on the other. So you could generically look at this like this, or we also have internal alkynes. And so that's where you have an R group on both sides of the triple bond. What we're going to see is there's slightly different chemistries for these and slightly different approaches to using reactants with these, because similarly to primary versus secondary versus tertiary carbons, we put this group out on the end, we're going to have different relative stabilities for intermediates, making this one have a slightly different reactivity than this. But we'll get to that down the road. But you just have to be aware when you're looking at an alkene, is it internal or is it a terminal? Yeah? Okay. So naming these things. Naming it when it's just an alkyne, pretty straightforward. When you only have an alkyne, you approach it pretty much exactly like an alkene. You just include the longest continuous chain, which houses the alkyne. You then number from the side, which gives you the lowest number for the alkyne. And then if you have, the only difference is, let's say if you're coming in from either side and you get the same number, what you do is you just then prioritize the side which has the lowest numbered substituent. So what happens if you don't have a substituent on either side that differentiates it and the alkyne is in the middle? It doesn't matter because it's symmetrical. Okay, cool. Everyone's awake. They had their coffee. Excellent. And then, just like before, you list all these substituents in alphabetical order after numbering based on that system. So it's actually nearly identical to alkenes, except that you're substituting Y and E. So let's do an example. Oh, drawing these in shorthand. I'm getting sick and tired of doing C's and H's. So I'm going to probably, as we get more complex with our examples, start drawing things in stick form more often. So we've already talked about the differences between drawing in trans alkenes versus cis alkenes. Well, for alkynes are linear. The triple bond is 180-degree bond, and it's sp hybridized. So to do that, what you end up having to do is something like this. This would be a dimethyl. So you'd have literally methyl on both sides of the alkyne. Now, if you want to draw this with structure from other pieces that have tetrahedral centers, you want to go back to this kind of motif. What you end up doing is something like this. You don't want to try to, you will occasionally see that. That's really not good form, because that's implying you have the ability to put things down here, which you don't, because it's a linear system. So when you're drawing in an alkyne and you're using the stick form, it's best to differentiate it. Now, if you're going fast, you have to take care to do it, because if you're going fast, you do this. Is that a methyl, a carbon, and a methyl, or is it just a sloppily drawn triple bond? I really didn't have any intention when I did it. I intentionally did it ambiguously. So, but you could interpret it either way. And because of that, during free response questions, students will argue. They're like, oh, I don't remember which one it is, but I'm going to do this, and then I'll be able to argue unsuccessfully that this was something that it wasn't. So go ahead and hit a hard pause, give yourself a little separation, and then continue on. If you're drawing in a triple bond with stick form.
Does that include 4 carbons or just 2 carbons?
If it's just 2 carbons, if it's just acetylene,
yeah.
If it's just acetylene, you can probably take the time to do that versus just drawing a triple bond.
Okay, so what you drew was 4 carbons.
That would be like me.
Space in there is 4 carbons.
Well, I could have, yeah.
Okay, that's what I'm
let's say instead of this, which is a little bit more clear, but you still don't see an interruption. It's clearer if you have a little interruption in the series versus something like that when people are in a hurry. So
the space indicates.
Yeah, I like it, a little pause makes it more clear.
Okay.
When you're drawing it out. So let's do. Then I had to say all that because I'm going to do. So let's name this thing. Longest continuous chain containing the alkyne, 1, 2, 3, 4, 5, 6, 7, 8. So we've got an octine as our base. We are going to see 1, 2, 3, 4, 1, 2, 3, 4. So it's equidistant from both sides. So we have to prioritize the side with the nearest substituent. So we'll come in from 1, 2, 3, 4, 5, 6, 7, 8. That gives us a 2-chloro and a 3-bromo. We need to prioritize in terms of order of names the bromo because of alphabetical order. So we'll have a 3-bromo, 2-chloro, 4-octyne. Let's do a different one. So for this one, what's our longest chain? How many cars?
7.
Ah, all right. Do we votes for 7? Votes for 6. Aha, okay, excellent. Because this is a bromine, this is your last carbon, and what's implied are your 2 hydrogens that you don't have to show because we're drawing it as a skeletal structure. So we've got 1, 2, 3, 4, 5, 6 carbons. So this is going to be hexyne. Distance from terminal carbon, 1, 2, 3, 1, 2, 3. So they're the same distance again, which means we have to go with this being our 1 carbon because it's the lowest numbered carbon with the substituent. 2, 3, 4, 5, 6. So we've got a 1 bromo, 5 chloro, 3 hexyne. So nothing too crazy. What happens if we have more than 1 triple bond?
I was curious, would it be diene or would it be dine?
Diene.
Cool.
Yeah. It's a whole class of polyenes. Yeah, where you have, and here's the fun thing about polyenes is you can't have multiple triple bonds to the same carbon because that's 6 bonds to a carbon. So all polyenes have to, at their highest density, be alternating. Where you have a single bond following your triple bond always. It's not like double bonds where you can have a carbon with a pair of double bonds on both sides. So yes, these are all a class of polyenes. And it's just like polyenes, except that it's diene, triene, etc. And so if we're going to name one of these, whoop, that is not right. Let's change it up. Well, I don't want to draw a lame structure, so let's do a good one. Something like this. We've got 1, 2, 3, 4, 5, 6, 7, 8 carbons, so we have an octyne. And if we were numbering from trying to figure out which side gets priority for our triple bond, we have 1, 2, 3 carbons for this triple bond, 1, 2, 3 carbons for that triple bond, but we have a methyl here. So we're going to come in from the side with the lowest numbered substituent, which is that methyl. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be a 2-methyl, and coming in from the side 3 and 5, numbering through the beginning of the ines. Octadiene. So far, no real departure from what we've done previously. We're just substituting ynes for enes so far. But this is the chapter where the book decided to make it fun. Yeah?
So you do include the A when you're naming it with ynes? Because you cut it out when you do with enes or names?
When you include the die, you do.
Oh, okay.
Yeah. Yeah. Other would be yeah. Yeah. But we're going to be throwing out, well, don't worry. I'm going to talk about something that we will be throwing out in a second. Yeah, so for the die, you have to have the A in there. So what happens if we've got both double bonds and triple bonds in the same compound? Yeah! Well said. Somebody just somehow summed up everyone's feelings in one moment of illness. Okay, both double and triple bonds. And not only this, what do we have? What do we do if we have other functional groups too? Like alcohols or amino groups. Or yeah, we can cry. That is one tactic that is absolutely legitimate. It happens in science and particularly in OChem. So it's okay, we've all done it. Or will eventually. But doubles and triple bonds are where we're going to start because they happen to have equal priority. I guess I'll just skip ahead right now into prioritization. If you're prioritizing functional groups for nomenclature, it's based on a degree of oxidation of that functional group. So carbon double bound to oxygens are going to have our highest priority. They're going to be right up there with alcohols, which are going to be a little bit more than our amino groups, which are going to have higher priority than our double bonds, which are equal to, this is equal to, not another pair of bonds. Triple bond. So, in some ways, it's actually a little bit easier when you have these other groups. When you have equality to the relative degree of oxidation, it's not totally the same, but or in terms of the reactivity or the degree of oxidation, but in terms of nomenclature rules, they're set equally. So we have a set of rules for how to handle these two together specifically. Yeah?
Can we just real quick reminder of what degrees of oxidation means?
Yes. So oxidation is loss of electrons. So this carbon is going to be more oxidized because of the presence of that oxygen being attached to it. Because of that partial negative charge being going up this way, so it's losing its electrical density, which is why that particular group's oxidized. And this is going to do it more powerfully than this, which will do more powerfully than this.
Oh, okay, that makes sense.
No problem. So back to the beginning, now that we've talked about priorities for different functional groups, what if we got both doubles and triple bonds? What you have to do is you need to identify the longest continuous chain which contains both of the functional groups. So both the double bond and the triple bond have to be included in your longest continuous chain. So I'll write it down. Once you've ID'd the longest chain, you number the chain. I'm just going to read it because it's a little convoluted. You number the chain indicating the location of the first stated functional group, usually placed before the parent chain, and you number for the second immediately before the suffix.
Can you repeat that, please?
That's not going to make any sense for me saying it, so I'm just going to do one, and it's going to make sense. Trust me, it's Awful. You're like, what's the parent chain? What's the suffix? This is ridiculous. You're right. So let's say we've got this relatively simple example. We've got 1, 2, 3, 4, 5, 6, 7. So we have a is it heptine? Is it a heptene? It's a heptanine. I know, right? We just did something fun. So we'll get there. All this jargon about parent chains. When you have a double bond and a triple bond, to deconvolute what the book's saying, you're going to list the ene first and the ein second. And as part of listing the ene first, we're going to get rid of the e on the end. And then we're going to number the ene before we title the parent chain. So in this case, this will be a 1, 2, 3, 4, 5, 6, 7 carbon system. This is going to be a 5 hepten 1 ein. So when the book says the first thing named is numbered before the parent chain, that's what they mean. Right before you designate the number of carbons in the parent chain with hept or oct or whatever, that's where you put the number for where the ene goes. And then the 1 for the ein, or secondly named functional group, goes right after the n. And the reason we have to break these numbers apart is because it tells us which one is where. If we start to put, if we said this is a 1,5 n ein, you wouldn't know which one was which. And heaven forbid, it was a di-n ein, and we had another number in there. So by breaking these up into 2 different locations, we have control over where we designate the number. Let's do another one. Getting ahead of myself. So for this one, we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got an octane ein, because it just has a double bond and a triple bond, and we're going to have, and you're going to, if you get confused with this stuff, if you just think of a double bond with triple bond as an E9 or an N9, it makes a lot more sense. It's not going to be an ein. You just kind of get used to saying an ein for these scenarios. It'll help dictate which one goes where.
Alphabetical.
Yeah. And I think it's partially just because it's easier to, I don't know if they did, I swear they did it because it's easier to say. Maybe, I don't know. That would make arbitrary sense. If you're trying to, like alphabetical, maybe. That would also make sense. Hadn't thought of it that way before. But we've got a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain, which includes both of the functional groups. We're coming in from this side because we're numbering to have the lowest number. Oh, and that's a nice difference. It doesn't matter which of the functional groups is closest. We started from this side because it was closest to one of the 2 functional groups. Because they have equal priority, whichever is closer is the side we start from. In this case, it's closer to this side. So we're starting, even though it's a double bond versus a triple bond, it doesn't matter because they have equal priority. Yeah?
What if you had the ene on the end? Like you have on the first example there, you have the triple bond on one end,
Mm-hmm.
the other end was a double bond, and there were no substituents like in this example. How would you?
Because you always name it as an ene ein, in those scenarios you're going to still put the this is the second named in I believe. when you have that symmetry. Let me go through the rules here. These are shorthand rules. Yep, if it's the same, you prioritize the double bond for numbering. So you go with the double bond first if you have the same distance. So if it had been this would have been 1, 2, 3, 4, 5, 6. So in this case, we've got, let's see, an octane something ein, and it's going to be a 5 ein and a 2 octane 5 ein. Once you do a few of these, it will get pretty easy pretty fast. You just need to get comfortable with breaking the numbers up so that this number describes the ene and this number describes the ein. And once you've done that a few times, it'll get pretty automatic. Let's see. Okay. So what happens if we have functional groups other than double bonds and triple bonds? Well, then we have to go to our list of prioritizations. So when we're designating what side we're numbering from, you're going to prioritize the side that gives the highest priority functional group the lowest number. So in this case, we would number from this side because it will give the hydroxyl group the lowest number versus coming in this side. Additionally, let's say we had something like that on the ring. The highest functional group on the ring is automatically going to be the one position on the carbon on the ring. So we're going to be naming this as a alcohol because it has a higher priority than the alkane. And we haven't described how to do alcohols, more complex alcohols yet. We won't do that until the very end of the semester, I think, after we do a couple more chapters. But it's pretty easy. It's just ends in all, right? So let's go ahead and look at one of those examples, or a couple of those examples. I think I might have just drawn the same thing backwards. Nope, I didn't. There's no methyl over here. So if we were going to name this, we've got a 1, 2, 3 carbon chain. We've got a hydroxyl group, so we have an alcohol that has to end with all. We've got an alkene starting at the second carbon. So this is going to be named similarly to what we did before, where we've got a 2 propen 1 all. We're always just going to keep the double bond right there on the beginning. Separate the numbering scheme so that this number, the ene, this number's the highest priority functional group, which is the main identifier for what this is. And then if we had substituents, we'd still be putting the substituents out in front. So if this had a methyl here, this would be a 2-methyl, 2-propen, 1-all. Yeah.
So the functional group with the highest priority will always be at the very end of the
Yeah. Unless they're equal in which case is our double bond, triple bond, and then the triple bond will arbitrarily get named as an yne here to keep the N here. Let's do another one. Longest continuous chain containing both functional groups, starting with the 1 carbon because we've got our hydroxyl on this side. 2, 3, 4. Curveball, throwing it up there. Why not, right? So we can play with it a little bit. So we do have a methyl group we have to name. On the 4 carbon, we've got a double bond on the 3 carbon. We've got a hydroxyl group on the 1 carbon. So this is going to be an N-all also, which has a modifier. We already did that. Here. That's more fun. I don't know why, I just can't use methyls for every example. It doesn't matter though. So this is going to be 4 bromo, because we got that out in front. Got to name the location of the double bond first. 1, 2, 3, 4, 5. Hent, what's the next thing? N. This is an amino group. So that's going to be our 1, 2, 3 to keep the number down as low as possible versus a 1, 2, 3, 4. So 2, 3, 4, 5, 6. So this is going to be a three because we have to name the N at the beginning. Cyclohexane amine. Why no 1? Because that's by definition the 1 carbon because it's where it's attached as the highest priority group.
Will you mark down if we put the 1 or just
Totally. Minus all points. No credit. Unless it's multiple choice. If there's multiple choice between having the 1 and having no number, then it's an all or nothing proposition, and it's more correct to exclude the 1. Yes?
If you had a methyl group where 6 is at, would you give that preference over the double bond because it's a smaller number?
Nope, because this is not a functional group,
Okay.
this is substituent.
Okay.
So that would be a 6-methyl. Yeah.
But if you had an amine and an alcohol,
A what?
Alcohol primary.
an amine and an alcohol,
Alcohol gets priority because it's more oxidized.
so how would you structure the name?
So you mean all?
But then, yeah, where would the
Oh, if we have 3 functional groups?
so then would we put the amine the as like a sub?
The good news is, and I think you're the one who asked the question about multiple functional groups in the beginning. I'm like, hey, we're addressing the question like 4 lectures later. Now I'm going to have to do the same thing to you because we don't actually have the chapter on amino naming nomenclature or alcohol nomenclature yet. So we don't have the tools in our toolbox to put all of them together yet. So we're going to have to wait until we get alcohols and amines. Sorry. But this keeps coming people back for more lectures, right? If we didn't leave cliffhangers, you're like, what happens when we have 3 functional groups? I know, everyone's just like so excited. It's not, oh, it's like, wow, that finally did her in. That was the end. I actually had a friend who pulled an all-nighter before Calc 3, and he was sitting basically right here. And he was falling asleep, and he was trying not to, because the professor was lecturing. And I've told the story of Van Veldhuizen, how amazing he was, but the guy was bobbing. Like, he was catching himself, and then he'd start to fall asleep. Before he'd catch himself, he'd snap up out of it. So Van Veldhuizen walked right up in front of him like this. He had his papers, and he's like trying to keep him awake while he's lecturing, like right in his face. At some point, Zach just fell asleep. And bam! Like right off the table. Like eyes popped open. And Fedfeldhuisen's like this, and Zach kind of shrugs and put his face down on the table and fell asleep. Stayed asleep for the rest of the lecture. Everyone, the bell rings, everyone leaves. Still out cold. Next class comes in, dropping their bags, being all chatty, still out cold. I don't know how long he slept, because we all went to breakfast. But, yeah. But he didn't join us for breakfast, so I think he might have stayed asleep for a while.
Still there.
No, unfortunately, no. He was back playing guitar terribly in the lounge later that evening. So
Oh, okay.
I know he survived.
That would have been funny if he just stayed asleep there.
I know. No, that would have been 2 deaths in the same class.
Oh my god!
First the professor, and then So now onto the fun things around alkanes, chemistry, right? Now that we can name them. Yay. So first we got to talk about structure of alkynes a little bit. I keep saying alkanes because I haven't had my 3rd cup of coffee yet. So a couple quick points. We are dealing with triple bonds now. So what this looks like in terms of hybridization is to do a triple bond, we have to have sp hybridization on the carbon and 2 non-hybridized p orbitals. Because you can't form a pi bond unless you have a non-hybridized p orbital pair which can align so you can share the electrons across the sigma bond. I guess it's a good point to point out we have our first bond is a sigma bond, and then we have 2 pi bonds as our second and third bonds. So this is our first bond, and our second and third bonds are pi bonds. So what this looks like is, I can use colors. So the first bond is our sigma bond. It's going to be our sp-sp. These bonds are particularly short because they have more s character proportionately than previous hybrids. So before we have sp3, which is 25% s character, sp2, which is 33% s character, and now we have 50% s character in these hybrid orbitals. So these electrons are held very close to the nucleus, which gives you even shorter, tighter bonds for your sigma bond here. And then the second and third bonds are going to be electrons being shared across those non-hybridized p orbitals, which are exactly 90 degrees apart from each other. And just like your double bond, this is a rigid system, can't rotate, because to have these electrons share through space, these p orbitals have to be aligned. Once you start sharing electrons, to rotate them out of plane, you functionally have to put enough energy to break 2 pi bonds. So it's going to take a lot of energy to rotate that bond. Yeah?
Would there still be, when the sp orbital is bonded like that, is there still the node on the opposite side?
Yes. Yeah. I don't have my stuff set up right to show it. And what it's doing depends on whether it's doing another hybridized orbital on the other side with another carbon, or if it's got a proton, which is not hybridized with an S or something like that. Other important characteristics, this bond, triple bond, is shorter and stronger than your classic double bond, but it's not like the double bond is not twice as strong. as a single bond. This is not 3 times as strong as a single bond because the sigma bond is significantly stronger because of the efficient sharing of electrons directly between the nuclei. So you're getting a stronger, shorter bond, but it's not 3 times as strong as a single bond. Did I have a question back over here? Did somebody had a hand up? The story of sleeping just totally did. Oh,
I'm still gonna fall asleep at some point.
that's awesome. Okay, cool. I won't turn the camera to face you. You're anonymous. He's got it figured out though, because he's outside my peripheral vision. Because my glasses only come to here, and I'm actually pretty blind. So until I actually turn my head like that far, he's totally evaded me up until now. Yeah.
So, where those carbons are attached to another carbon or hydrogen, there's also an sp bond, right?
So let's do one. So this is fully hybridized as sp hybridized, sp hybridized, sp3 hybridized, s non-hybridized. So this sigma bond would be an SSP, SP sigma bond. This sigma bond's SP3. So you can always just look at the number of electrical groups surrounding the carbon, and it'll tell you what the degree of hybridization is. Because if it's tetrahedral, it has to be sp3. If it's linear, it has to be s2. If it's trigonal planar, it has to be sp2. SP. If it's trigonal planar, it has to be sp2.
So each of those has 2 sp.
Yeah, because when you combine these 2 orbitals, you always end up with the same total number of orbitals. So because we put one, when you make sp3, you end up with 4 equivalent orbitals from putting the s and the 3 p's together. If you do sp2, you've got a trigonal planar system, and then you have, looking down from the top, non-hybridized p, and you have 3 equivalent orbitals from combining the s and the 2 p's, and then you'll have 2 equivalent sp orbitals, 1 here and 1 here, for each sp hybrid. Yeah. Okay, so now we've got some of that done. Let's talk about reactivities. So if we were looking at an alkene and we put it in the presence of hydrochloric acid, we would have a nucleophilic attack where the electrons from the double bond attach the proton because of that partial positive charge, pushing the electrons to the chlorine, forming a chloride because it's pretty happy with all those electrons, and we would get our positive charge on the more substituted carbon. Based on that, what are everyone's expectations of that?
Would it do basically the same thing twice because there's 2 bonds, 2 extra bonds that get broken to react with the hydrochloric acid?
Yes and no. Yes and no. But we'll get into why yes and why no in just a second. Other people's impression, they're like, oh, well, we got a double bond, right? It makes sense. We should have these electrons act as the nucleophile and do the first attack on the hydrogen. And that is the yes, is you are getting your first nucleophilic attack, but there's some nuance to how it's happening because of the formation of the type of cation that we're going to form. So let's go ahead and walk through it. So what makes alkyne chemistry a little tricky, there's a couple things that are going to make it tricky, is the mechanism is going to be slightly differentiated from the alkene mechanism, even though how it starts is basically the same. And then there's going to be a second attack or a rearrangement, depending on what is being added. So, and there's going to be some unique stereoselectivity with how the second attack happens. So we have a couple different moving parts to make this a little more nuanced than what we were doing in the last chapter. So first off, let me let's just do it. Without adding the mechanistic detail, we're going to use the same explanation that we had before, where we have our first nucleophilic attack on hydrogen. This exceeds the duet, so as this bond is forming, this bond's breaking, pushing the electrons, forming a chloride, which acts as a leaving group, and we have this cation as an intermediate. This is not the same thing as what we would have had before if we were using the double bond analog. This is an alkyl cation, a secondary alkyl cation, and this is a vinylic cation. And the presence of these extra electrons next to it changes chemistry / stability. So some of you have probably read this. Is this going to be more stable or less stable than the equivalently structured alkyl cation? Less stable. Why is it less stable?
Because sp bonds are more electronegative. So
Yeah.
not having a positive charge.
That's why. Yeah. So this is sp hybridized still because of the vacant group. This is not. So this is going to have, because of the increased S character, more electrons close to it. So it's going to be more electronegative, meaning it's going to not like housing that positive charge even more than this one. So even if you don't have the explanation, or if you don't want to kind of go into the why so much, whenever you have a double bond on a vinyl or vinylic cation, it's going to be even less stable than this. So that is why, even more so, we have to put the charge on this location than the primary location, because if we were to try to put the charge here, it would be even less stable than a primary alkyl carbocation, which we already know is very, very hard to form, very unstable. So because of this, it's unlikely that we go through the same reaction mechanism, because before we were able to form a discrete carbocation on a secondary position. In this case, not so much. So let's take a look at how this probably forms. And let's just put in our group for generic things. So we have a terminal alkyne here, and we're going to put in our, how do I draw this? You're still going to get an initial attack, like what we saw before, but we're going to get a pi complex as an intermediate. So there's a lot of things going on here. We are breaking this bond to start to form a new bond here. So this bond's breaking, forming a new bond to the hydrogen. That's exceeding the number of bonds to hydrogen. Before, we would just kick that off and let carbocation form here. But instead, what's happening is you're getting a little bit of bond character to this carbon, and you're getting a little bit of bond breaking to this chlorine. And so basically we have a whole bunch of bonds kind of broken and kind of forming simultaneously. Just go back to this now. What do you guys think the outcome of having this pi complex intermediate versus the carbocation will be in terms of the products? Would you expect this to be subject to rearrangement based on a 1,2 hydride shift? No, because you don't have a discrete carbocation. And because you have this group here, what we're going to see is we're going to have stereoselectivity in the product. Son of a gun. Of course I can't use this example because I put a hydrogen there, so there's no stereoselectivity. You're going to have stereoselectivity in your product because of the one side attack followed by a second side attack off the opposite side. So all this mechanistic stuff aside, what happens if we now have more hydrochloric acid hanging around? We have an excess of hydrochloric acid for this reaction. Right. Now we have an alkene that's going to do a second attack. Right? Now, this alkene is going to not be quite as aggressive as it was before because of the electron withdrawing group here, pulling some of the electrical density off of this, making it slightly less nucleophilic. So even though this is an alkene, it's a substituted alkene, which no longer is quite as good of a nucleophile as it was. So the alkyne is slightly less reactive. Than the equivalent alkene, and this substituted product is going to be slightly less reactive than the equivalent alkene. So all these reactions are going to be a little less vigorous than they would be if it was just a non-substituted alkane. So let's just draw the product. We don't have to worry about our mechanism at this point. We have symmetry here, so where we put the first chlorine doesn't really matter. So this is first step. Where's the second hydrochloric acid going to go? Position A or position B? Votes for A. We have 3 hands, 4 hands. Votes for 5. We're gaining momentum. Votes for B. Oh, 2 hands. Votes for I haven't the foggiest freaking idea. Why do you do this to us? Excellent. Excellent. So if I were to draw in a mechanism and say, pick that off, and you had to place a carbocation somewhere, would it prefer the more substituted position or the, wait, they have equal carbon substitution. So,
There's chlorine in.
yeah, there's a chlorine there. What's the chlorine doing?
It's helping scramble it.
So is that electron withdrawing at nature going to increase or decrease?
It's gonna increase the stability.
Oh. Oh, here's the thing. Degrees of weight matter. So we have all these extra electrons hanging out around here. That actually helps satisfy the positive charge a little bit because of its proximity. So this is going to be preferred. So we're going to get the second attack here. So our product will be having both chlorides on the same carbon. And before, when we had them on opposite carbons, that was called vicinal, and this is called geminal. It's a geminal dihalide. So when we do the exact same, this is long story, short outcome. Whenever we have some generic, in this case, internal alkyne, and we are reacting it in excess hydrochloric acid, you're going to end up, ooh, I shouldn't do that because I'm going to do that because otherwise we'll have a mixture of products. A geminal dihalide is our product.
Is this one of the reaction mechanisms where you know the input, the output, and the conditions, or do you need to be able to sketch out all the steps?
Should probably be able to sketch this one out.
Okay.
So, do you want to do that real fast? So we put it all together in one big...
Yes.
Okay, we can do that. Second question, yeah.
So when you have a triple bond reaction like this, is it always going to end up being chiral? Or when you have...
That's not a chiral. Oh, I see. For this one, yeah. Because you're always going to be adding 2 of the same thing to the same carbon. So you're not going to have... well, you're not going to be developing a new chiral center here or here with this reaction. It doesn't mean that it will be achiral at the other locations. You're not adding a new chiral center with this one.
Which is like the first reaction HCl and the second HBr.
Right, if you have multiple nucleophiles, if we had HBr and HCl and play together, you'd have a nasty mixture of things. But hopefully we wouldn't be doing that. Okay, so let's just go ahead and do this whole reaction. Let's say we've got, we'll do a terminal alkyne. We've got hydrochloric acid. We're going to do our first attack, which is going to give us a little bit more room here. our pi complex. Pi complex is then subject to a second attack. So, oh man, this is super fun. What's hydrochloric acid do in aqueous solution? It fully dissociates. We have an excess of hydrochloric acid. That means we have, and just hanging out. Wow, there's a lot of motion here. This bond breaks to form this bond, and then this bond pushes electrons to this hydrogen, which exceeds the duet, which can then push off the chlorine, which shows why we have anti-addition for the chlorine and the hydrogen in this mechanism. And then we can come in with another equivalent of hydrochloric acid. This has to add here. Oop. Wait. Transition state. Okay. Cool. Good. Why is this one preferred? We talked about extra electrical density around here, but we could redraw this as a resonance structure. So this is a redraw of that first. It's not a super high quality resonance structure, but it is valid. Carbocations aren't super stable, neither are halogen cations, but this spreads cationic charge over multiple nuclei because we can share the electrons to form a double bond to carbon. So this stabilizes the positive charge by dissociating it over multiple positions. And additionally, this is primary, this is secondary. So we have two rationales for this one. But I can just do the second attack with the chlorine attacking the cation, and that gives us our product. So that's the whole mechanism.
So it's the resonance structure
Oh, no, you don't have to show the resonance structure as part of the mechanism for this one. It's just an explanation for why we're getting a same side attack. So if we did this on a terminal alkyne, if we did it on an internal alkyne, you run into problems because if you don't have a symmetrical internal alkyne, you're going to have multiple products. Let's take a look at what that looks like in the next few minutes here. So just kind of cautionary. If you've got something that looks like this, where the double bond's in the middle and you have a methyl on both sides, that's fine, because if we attack with extra hydrobromic acid, you're going to get the same product, regardless of which carbon gets the initial tap. Because if we tack this one first, it's going to get the second one. If we get this one first, this will get the second one, but they're going to be the same product because it's not a chiral center. If we have an asymmetric system, it's going to give us mixtures of products. Let's say this, where we have 1, 2, 3, 4, 5, 6, 7, a 3-heptine. If we do this exact same reaction on this compound, if we tack this position first, we'll get a dye substitution, geminal dye substitution at the 4 carbon. If we get this one, we'll have dye substitution at the 3 carbon. 4, 5, 6, 7, 1, 2, 3. There we go. So, totally different compounds. And both of them are totally valid, so you have probably 50-50 mixture of these two products. So as soon as you're dealing with asymmetric internal alkynes, you're invariably dealing with combinations of products, which is almost never desirable. Almost never. So there are some advantages to symmetrical internal alkynes and terminal alkynes in terms of a lot of our substitution reactions. One last thing, which we can tuck into the next 5 minutes. And we'll leave keto-enol tautomerization for next class. If we've got addition of a halogen, it's a 2-step process. We're going to get our first addition, followed by the exact same addition to the opposite sides. We're going to be chlorinating the daylights out of that spot. This does not give you a mixture of products. So if you do the exact same reaction we would do, adding a halogen across a double bond, it's just going to be times 2. And we're going to get 4 chlorines added across the 2 carbons now, instead of the 2. So this one's actually pretty intuitive. This is a good place to leave off. We're going to pick up with keto-enol tautomerization from addition of a water across an alkyne. Next class. So see you guys Wednesday.